Hello, welcome to my channel. Let's discuss about directional couplers in this video. So coming to the directional couplers, it is a 4-port network. Directional couplers are used for dividing power and combining power. So basically this is the general representation of a directional coupler where the opposite port of an input port will be throughput and opposite of isolated will be coupled, and input and isolated will be together. So for example, if I given here in this example, they are saying that input 1 is the port 1 will be the input, but if I take input third port as an input, how it will be? If this is an input, the opposite side will be isolated. Okay, isolated port like the other, like I mean the top one will be isolated because these should be together, and the opposite side of input will be port throughput. Okay, and here it is isolated, so opposite of isolated is coupled. So like in this way we need to see what will be the other ports if you are given input as the to the particular port, like that. So it will vary. So basically this is the general representation, and this is the symbol, this arrow, and like this is the symbol of directional coupler. And coming to the interior of this directional coupler, there is two holes. Okay, so how it will be, let us take a box, and here I will take two lines. Okay, there is one line, one more line. So basically what they are saying is the distance here. Okay, so this distance will be lambda g. Okay, so the distance will be lambda g by 4. Okay, so this from this what we can see, these are the ports. Okay, now let us consider this port like 1, 2, so 1, 2. So for our understanding, anyway, these ports are okay. Just it will be like 1, 2, 3, 4. Okay, 1, 2, 3, 4. So if I given 1, 2, 3, 4 like this, if I given this port as 1, and it will be 2, 3, 4. Okay, for example, if I give basically 1 and 4 will be one side, 2 and 3 will be one side, and 1 will be opposite of 2 like this. So now I am giving the input to the first port. Okay, I am giving the input to the first port. Now what happens? The signal goes like this. As there is a path here, it will deviate to this path, and this will be actually split into two parts. Okay, neglect this vertical height, only concentrate on the horizontal height. That means this distance. Here it is traveling lambda g by 4, and also here it is traveling lambda g by 4. That means totally how much distance it is traveling? Only so actually you think that this is also have some distance, and also don't neglect all those, only concentrate on only this part, only this part. And the travel, how much distance is traveled? Lambda g by 4 plus lambda g by 4, that is lambda g by 2. Correct. So for this is what for the second wave. I will take another color. This is the second wave, and this will be the first wave. Okay, I mean the first signal, second, like basically it is split into two parts, right? So first signal will suffer no distance. It is basically taken as 0 with respect to this. Now coming to here, or you can also say that with respect to this, like if I consider this is the extra length that is traveled by the second wave is only this part. No, that's what we are taking, only this length. So now what happens? Now let's find the beta L for this. What do you call beta L? Beta L is already told. Beta L is called electric length. Electrical length. So when coming to the electrical length, beta L can be extended as follows. Beta will be 2 pi by lambda here it is actually what is called lambda g means waveguide wavelength, waveguide is wavelength, and so this is also lambda g, where length is the total length traveled by the wave. So for the first wave it is traveled 0, so basically it will be 0. So beta L, we'll denote this as some equation 1 will take. And for the second wave, what happens? Beta L will be 2 pi by lambda g into lambda g by 2, right? So lambda g, lambda cancel, lambda 2 cancel, and you got pi. So this pi, what happens? Basically, if you observe, there is the signal 1 has 0 degrees of phase shift, 0 degrees of phase, but the signal 2 has pi shift phase of 5 degrees. That means they are totally opposite to each other. So when they combine to combine in this fourth port, what happens? This total net will be 0. So that's why this port is called isolated port. Now coming to the third port. Now let's take another example. Okay, I'll take some colors. Now take a length and I'll take this. And okay, let's take like this, and now take a signal. For example, once this signal is split. Oh, so let us take a signal, I think. Okay. Now let us take a signal. Basically this signal is sorry, pencil. Not let us take a signal, and it's going like this, and here what happens, it's got splitted here, and one more here also, it's splitted and combining here. So the first signal, so this first signal suffers lambda g by 4 distance, and this second signal only suffers lambda g by 4 distance. This is the second signal. So basically when you observe, basically both are suffering the same distance. No, that means there will be no phase change between them. When you calculate the phase difference between the signals, it will be same. Okay, so how to find the same beta L, and when you calculate 2 pi by g lambda g into lambda g by 4, it will be pi by 2. For the second signal also it will be pi by 2. When you find the difference between those two, it will be 0. That means they will get added. That's why it is called coupled port. Okay, so coupled port. Now coming to this through port, it is like nothing but the same wave. Let us take this okay, and slits. Okay, now what happens? This signal will be what is the signal that is going from here will pass it through here. That means there is no sorry. So whatever the signal that is sending here will be passed directly through this. Basically this is called throughput. So throughput. And now coming to, this is how we need to calculate for any couplers what is the phase suffered by the signal when it passes through. Okay, phase difference between, or if you want to calculate if the port is called a summing port or why it is called summing port, all this will be explained using this electrical length only. Okay, and coming to the next point, this is all I have told. Now we need to find the scattering matrix for the directional coupler. So we know that for the directional coupler is a 4-port network, and it is lossless, and also it is reciprocal and match at all the ports. So by using those conditions, I have made this matrix and solving the same using the conditions, that is lossless properties and all. What we got finally was this matrix. Where is this? So basically what happened, let's see the derivation part here. Some okay, so we got like this. Now applying lossless property for column 1, and we got these 3 and also this substituting, and we got a matrix like 0, S12, S13, 0, S12, 0, 0, S24, like this we got. Now applying unitary property again, what happened? We got all this. Now if a plane if the plane reference is chosen for the port S12 and S34, considering in a real time where there will be some phase change, because definitely there will be phase change, no? So that's why what they are taking was this S12 and S34 as alpha, S13 as beta into e power j theta, S24 is equals to beta into e power j phi. Okay, here S12 and S34 are taken as alpha relative to that, and so here we are taken as alpha, no, and these are as this, and where theta and phi are called different phase changes, So they are taken this kind of notation because the derivation of these terms can be applicable to any type of directional coupler. Okay, so depending on the values of theta and phi, there are two types of coupling of directional couplers. One, when theta and phi are equal to pi by 2. Okay, when these theta and phi are equal to pi by 2, so when you substitute this equation, like for example, like alpha will be not, so that won't affect. So only this term where theta and phi are there, so S13 and S24 will be affected. So when theta is equal to pi by 2, beta into e power j pi by 2, that can be written as e power j pi by 2 can be written as j. So S13 is called j beta. And also same for the here also it is the same, because when you substitute e power j pi by 2, that value will be j, so j beta will come. So in the manner, if I substitute theta is equal to 0 and phi is equal to pi, what happens when you substitute 0 in e power j theta is equal to 0, that means it will e power 0, that means 1 only, no? Okay, when you substitute e power j pi means 180 degrees, so it will we will get as minus 1. So substitute these values in the general form here, and we will get the matrix of this. Okay, so these are the two combinations possible for lossy property. One take both like what we can conclude from here is to have a lossless coupler or a to satisfy the lossless property by directional couplers. The only two ways are there. Either we have to give theta and phi as 90 degrees, or other we can take as theta is equal to 0 and phi as 180. Now basically alpha and beta are same real values which are depending on the design on the directional couplers. There we add the values of theta and phi, it should be equals to 180. So theta plus phi should be always 180. One is the property, and another is the amplitudes of alpha and beta are not independent. So basically what happens, they are dependent only. So how they are dependent? The amplitudes of alpha square plus amplitude of beta square should sum up to 1. So quantities or parameters used to characterize a directional coupler. What are the things that you are will be taken into account to find if to define a like directional coupler? So one is coupling factor. So what is the coupling factor? So coupling factor is like simply in simple terms, coupling port. What is the coupling port? Third port, right? When you taken one as an input. You understand it? When I give input to first port and I am taking through to second port, isolated port is 4 and coupled port is 3. In this way, what happened? So in this way, what happens? Now, if we take this third port is a coupled port, C is equal to minus 10 log P3 by P1, right? So now substitute what is the P3? The average, no, 1 by 2 incident minus reflected. In this case, with respect to input, B3 will be the incident. So B3 square minus A3. As A3 is equal to 0, 1 minute. Yeah, because why A3 is equal to 0? Because it will satisfy this condition. No, all ports are matched. That's why we will take A3 as 0. You understand, no? So while substituting P3 we got this much, and P1 is the how much you got. P1 is equal to, because S11 is also 0 because port 1 is also matched. So P1 is equal to 1 by 2 A1 square Now substitute in this, and C is equal to minus 10 log of this, and substituting the values, what we got, minus 20 log B3 by A1, that is minus 20 log S31. For symmetric coupler, S31 will be beta, correct, as we found in the above situation. In the above case, what is the S31? It's beta. Sorry, for symmetrical, no? Wait, I think yeah, mod S31 will be beta. Actually, to speak, it is mod only, so S31 will be beta. So here it is. And for an anti-symmetric also, it is beta only. Actually, if we, to be frank, if you want to say it is like J beta, but we have to take the mod value, no? That's why it is beta. So anti-symmetry is only directly and anyways it is beta. So that's how we will derive for this decibels. Now isolation. What is an isolation? Isolation represents the measure of power delivered to the isolated port. Okay, how much power? So the general formula is minus 10 log P4 by P1, because P4 is the port 4 is the isolated port. That's why power transmitted to the port 4 by power given in the port 1, input port basically. So in terms of S parameters, if you write this P4 as 1 by 2 mod B4 whole square minus mod A4, okay, this is the general average formula what we discussed. According to the port 1, this is the incident, this is reflected. So as the all ports are matched, so A4 will be 0. So from that P4 is 1 by 2 mod B4 square. So like that, P1 is this half A1 square. So from that what we got, I1 is equals to minus 20 log mod S41. Okay. Ideally S41 will be 0. Okay, but practical there will be some leakage signal. So S41 is equal to 0. Why? Because why S41 0 ideally? Because what we derived here, when I given an input, see, when I give an input here, what happened? These two will be split and it travels the lambda g by 2 distance, and after that the phase difference is 0 and pi, and they got summed up and summing up to 0. That means ideally there should be no signal coming out of here, but due to some imperfections or some losses, leakage signal, so there will be some, it won't be 0 practically. For ideal coupler, isolation is infinite. Why? Because we got this as S41 as 0, no? Log 0 is infinite. So, but practical coupler isolation is high but not infinite. That's it. It will be high but not infinite. Directivity. So directivity can be seen as D is equals to minus 10 log. Directivity is the it is the ratio of power delivered to isolated port to, and basically the difference. We can say it as a difference, like what you call, it's the measure of coupler's ability to isolate the forward and backward waves under coupled and uncoupled ports. Okay, coupled and uncoupled means coupled will come, sorry, coupled port will be there and uncoupled will be like isolated. That's all. So the powers distributed, that is difference between the powers distributed for these two ports. So that's why it is like isolated this. So directivity represents in S parameter. So basically we can write is like P4 by P1 by P3 by P1, where we got already P4 by P1 is S41 and P3 by P1 will be S31. Ideally coupler directivity is infinite, because again S41 is 0, then couplers directivity also become log 0, that is infinite. Coupling and isolation and directivity. Coupling, isolation and directivity are mutually dependent on each other. So how can we write? This is the formula. Isolation is equals to coupling for directivity in milli, like the units for them, they are calculated in milli dB. That's what they wrote here. Generally I is equals to C plus D. That's it. So these three quantities are important for characterizing the directional coupler. So let us take an example. Here it is given like I is equals to minus 10 log P4 by P1, and directional coupler offering of isolation of 40 dB and directional coupler offering the isolation of 60 dB. So we need to find which one is the better. Okay, I am giving a power of 1 watt. So for DC one, like directional coupler 1, what is the values? 40 is equals to minus 10 log P4 1. P4 is equal to 0. milliwatt. That means the power output over the isolation port is 0.1 milliwatt. Remember in isolation port we need to get as low as power as low as possible. Okay, the power coming out of the isolation port should be as low as possible. So what we got here, 0.1 milliwatt. Now coming to the second directional coupler, which has a isolation of 60 dB. 60 is equals like this, and P4 is equal 1 microwatt. Obviously this value is less than this one, so we need this type of directional coupler only, so we'll prefer this one only. So basically so that's it. Like the power offered was 1 microwatt, which is very small compared to this. Next problems, coming to the problem, a directional coupler has the S matrix given below. Find the directivity, coupling, isolation and return loss at the input port when other ports are terminated with matched load. So they have given already S matrix, so this is okay. After this, what I have to do, C is equals to, we know that for coupling, the formula of coupling is C is equal minus 20 log mod S31. So mod S31 and S31 is 0.1, we got the value, and I is equals to minus 20 log mod S41, and we got this value, and D also we got this. So return loss, for the return loss, what is the formula? Minus 20 log mod S11. So this return loss formula will be set in the first video. Insertion loss, return loss, all this will come in the first video itself, so you can check it out there. And minus 20 log of 0.05, and we got this value. So next, coming to the hybrid couplers. So what is a hybrid coupler? Hybrid couplers are there, basically they will be looking like this. Okay, so in hybrid couplers are the special case of directional couplers. It has coupling factor of 3 dB. Okay, so they already told that C value of is 3 dB. From this, if you calculate alpha, how can you calculate alpha or beta? Because basically, so coupling is minus 20 log of S31, where S31 is equals to beta, right? As we discussed. So what happened? Alpha is equals to beta is equals to 1 by root 2. Like for the symmetrical, even if it is symmetrical or anti-symmetrical, this one, wait, I had it out here. So now 3 dB. So by calculating here, alpha is equal, beta is equals to 1 by root 2. As we know that alpha square plus beta square should be 1. From that, alpha is equal to 1 by root 2. So from this, what we can observe, since 3 dB represents the reduction of signal amplitude by 1 by root 2 on its terms of power, it represents the reduction of power by 1 by 2. So in terms of signal amplitude, it will reduce the signal by 1 by root 2. Okay. If we represent in terms of power, it will reduce the signal power by half. So quadrature hybrid. So in the quadrature hybrid, it is an example of symmetrical coupler. Okay, it has a 90 degrees phase shift between port 2 and port 3. As it is stated, is symmetrical coupler, theta and phi will be pi by 2. Okay, so what is the S matrix for this? 1 by root 2 times of 0 1 j 0 1 0 0 j j 0 0 1 0 j 1 0. This is the S matrix for symmetrical hybrid coupler. So quadrature hybrid coupler is also called as branch line coupler. Okay, in this branch line coupler, the diagram will be looking like this, where the path distance are like this distance and distance should be considered. So this is L by 4 and the vertical length is also L by 4. So the impedance of these leads and are Z0 Z0, so Z0 and Z0, and this vertical in this square, this vertical length also Z0 and Z0, but this horizontal sides are Z0 by root 2, Z0 by root 2. So that you need to remember. And this is constructed using microstrip technology. So I already told what is microstrip technology in the previous video. So microstrip technology is nothing but this is like a copper strip. Okay, simple copper strip placed on some substrate. That's it. So Okay. uh, so for that, the S matrix for the branch line coupler will be this one, minus 1 by root 2 0 j 1 0 j 0 0 1 1 0 0 j 0 1 j 0. So don't confuse with those two. This is branch line couplers matrix and this is the symmetrical hybrid couplers matrix. Okay. Now coming to the work is same what we told. For example, for the above S matrix, the signal coming from port 1 to port 2 has a phase shift of this much, and the signal coming from the port 1 to port 3 has a phase shift of this much. So the relative phase difference of 90 degrees present between signal coming from 2 and 3. Okay, that's what. Like this you need to find the relative phase difference. Okay, let us see how the fourth port is getting isolated. So same way, we'll just, it is traveling lambda g, and here it is traveling lambda g by 4, and it is traveling lambda g by 3 lambda g by 4. So when you solve this, and we'll get pi. Okay, the different phase difference will be pi between those two ports, first path and second path. This is pi. Okay, and so okay, next thing is signal which is coming directly to the fourth port, and the signal following the outway which path length has 3 by 4. Okay, so this is 180 get cancelled out, and this is what you have. And the third port is all. Let us see how much signal is coming to the coupled port. So how to send, find here is lambda g by 2 and it is lambda g by 2, like that. So part 1 and part 2 has a phase difference of 180. So both phases having some phase difference. So at the end they will get added up and it will be come out of the port 3. So next thing, when the signal is coming from port 1 and port 3, it will have a phase shift of 180. Depending on the design frequencies, lambda value is obtained. Yes. Okay. Next, magic T hybrid or rat race hybrid. So it is an example of anti-symmetrical coupler. Okay, the magic T hybrid and the rat race hybrid is an example of anti-symmetric coupler. It has a 180 phase shift. Okay, actually it has an it has a 180 phase shift difference between port 1 port 3 fed at the port 4. Okay, initial here previously how much it is there? It is 90 degrees phase shift between 2 and 3. Okay, so that's what. So rat race, like so that's why 180 phase shift. No, that's why what this is the S matrix for rat race hybrid or the magic T hybrid. So basically this rat race hybrid is also called as 180 degrees hybrid. So let's see what these ports will have. So these are 4 ports. One port, first port is called summing port, the other port is called the difference port, normal 2 ports, 2 and 3 ports. So symbol for 180 hybrid, so this is the symbol. Rat race hybrid working is similar to magic T working, so it is called a magic T hybrid, so it is called as magic T hybrid. Whereas magic T is constructed using microwave devices, but rat race hybrid is constructed using microstrip lines. So microstrip lines means the copper strips cut, the copper sheet will be cut into this strip. This figure shows how the rat race side look in the real time. So basically there will be ports, the difference, the path length is of lambda by 4, and the path length for first port and third port is lambda by 4, third port and fourth port is lambda by 4, and fourth port to second port it will be 3 lambda by 4. No, it is also called as ring hybrid, so it is looking like a ring, no, so it is also called as ring hybrid. Now coming to the S matrix, if the ports are changed, the S matrix will also change. So but this is the value, this is the matrix for when this port is first port, second port, third port and fourth port. Okay, don't interchange the ports. For this particular arrangement of the ports, what are the corresponding values if you given the input to any one of the port. Now the transmission line is associated with the fourth 4 ports have a characteristic impedance of Z0. They are telling that all these ports, okay, apart from the ring, only these right strips will have Z0 impedance, but coming to the ring, it will be root to Z0, okay, whereas the entire ring has a characteristic impedance of root to Z0. In rat race hybrid, one of the port acts as summing port and other acts as a difference port. The first port acts as summing port and fourth port acts as a difference port. Here the length between port 1 and port 2, port 1 and port 3 and port 4 has a length of lambda by 4. As I told you before, this is what they are explaining again, and on port 2 to port 4 it will be 3 lambda by 4. Okay. This specification should be followed as the same, otherwise the above S matrix will be different. If we didn't mention, like we didn't follow this length. So also even odd mode analysis is used to derive the S matrix. So even odd mode is another mode of analysis. So where is used to derive this S matrix. So for now no need. And so what happened in the S matrix? It is minus. This is S matrix, no, for okay, ring rat race hybrid. Now consider a case feeding input to port 1 and coming to port 2. It has 2 paths. So I am giving input to the first port. What is the output at the second port? So first port follows the port path 1 and path 2 pi by 4. So second path will be port 1 and port 2 by passing through the ring, and this is what we got. The first part is 90 degrees and the second part is 90 degrees only, so there will be are in phase. Okay, so therefore the two paths are traveling in phase and the family get added up together because of we are having a signal at second port when we fed the first port. So what they are saying, when we fed the signal at the first port, they will travel all around this, and another path is this, another path is this. These two will be added here because they both have same, okay, they both have same phase. Now coming to okay, same for the signal out of the port 3 also. So the first path will have a length of lambda by 4, the second path will have lambda by 4. Same like port 2 and port 3 also will get the signal which is added up from port 2. Same like port 2, port 3 will also get the signals which is added up from port 2. For the signals coming from port 1 to port 4, it has two paths. First path is lambda by 2, second path is lambda. So lambda by 2 is equals to pi and lambda is equals to 2 pi. So basically what the difference is pi, no? So this is they will be in this fashion, 180 degrees of then. So these two signals get cancelled out. So no signal will be flowed to port 4. So summing port. Here we give the input to the second. Now why it is called as summing port? If we give inputs to port 2 and port 3, what will happen? They will get added up in the first port, and if you see for the fourth port, they will get subtracted. So that's why that is called difference port. So now coming into the problem, if they are asking like the normal substitution, there is no that much depth is there, but only one thing you need to remember is if you want to convert this into dB, from dB to milli dB, we just need to add plus 30 degrees to it. If you want to convert this into micro dB, then we need to add plus 60 to the value that is gotten. If for example this is 3.01 dB, I want to convert it to milli, then it will be 33.01 dB. For example, if I want to convert it to micro, it will be 63.01 dB, like that. So insertion loss, okay, they have given that, and just expansion and solving normal numerical problems, the same. So basically, actually here in the question they didn't mention about the matching the fourth port, okay, but what happened, the question given us two identical 90 couplers and C is equal to 8.34 dB are connected as shown, which resulting in amplitudes and phases at 1 minute. So now coming to this, here you can see in the question they didn't mention anything, like they just mentioned the coupling factor and our connected system as shown. Find the resulting amplitudes, phase at port 2' and 3' related to port 1. What is the phase of and amplitude they are asking. So in general they are matched at all the ports. Now that's why actually they didn't mention anything about fourth port. Like see, the first port is given as input, so okay, and the third and fourth will be connected in this fashion, and third is like this. Third 3' and we need to find the values at 3' port 3' and port 2'. So nothing is given about the fourth port. So what we'll do, this is as a match. Anyways, it is matched only. That's so we are just mentioning that here. So both are 90, like input signal is given at port 1 and matched load is connected to the fourth port. So both are 90 degrees coupler, that is they are symmetric couplers. Okay, why? Because they have given that they are 90-degree couplers. No, so 90-degree couple means theta and phi will be 90, and they are matched. Now coming to now coming to the coupling factor, that is 8.34 dB. We'll just convert it into beta. We got is beta as S31. No, that is beta, that is why 0.383, and alpha square plus beta square will be 1. So from beta we can calculate alpha, that is 0.9237. Now assuming that we are giving an input voltage of having an amplitude of 1 and a phase of 0 degrees to port 1, what happens? So this is the for the 90 degrees, we know that this is the S matrix. So for the S matrix, we know this, the equation will be V minus is equal to S into V plus. From that we got this, and what we have to know, and again we know that assuming V1 plus is 1 volt, like we are assuming, that's it, we are assuming that input voltage is 1 volt at an angle 0 degrees, as port 4 is matched. Okay, so V4 plus will be 0. Okay, that's it. So because same like A4, no, A4 is called V4 only, V4 plus, so that's why V4 plus is 0. Now V2 minus is equals to, from the matrix multiplication, what we know, what we'll do, we'll find V2 minus. So because okay, because see this we need to find this second and third ports, right? For the because first we need to find the inputs that are going for this box. So those inputs are the outputs of this box, that is 3 and 2. So we need to find those two parameters first. So V2 is equals to alpha into V2 plus J beta into V3 plus. So as V into with okay, J beta into, oh sorry, this row, no, V2 minus alpha into V1 plus J beta into V4 plus. So V4 will be 0. So alpha V1 plus, so what will happen, V1 plus already we are taken as 1 volt at an angle 0 degrees, and alpha we found that 0.9237. We substitute and found that V2 minus will be this one. Similarly we will find V3 minus. So V3 minus will be this, V3 minus is equal to 0.383 at an angle 90 degrees. So okay, now what I have to do now for the second directional coupler, that is the second one. This is the matrix, okay, same matrix, but we will have dashes here. So we need to find what are the values we need to find. This one. So why are you only finding the negative, that not positive? Why are you only taking the minus one? Because those are the only things that are going outside. Because if you take plus, that will be in this direction, right? But the negative value will be in this direction. That negative in the sense V2 minus and V3 plus will be in this direction. So we are only interested in this direction, right? Because those only goes to this box. So here also those only will come outside. So here also V3 minus dash and V2 minus dash will only come outside. That's why you're only concentrating or interested in finding this reflected values. So V2 minus is equals to, from this above expression, V2 minus is equal to alpha into V1 plus dash and plus J beta and V4 plus 1. And also we know that V1 plus dash is equal to V2 minus, because I told you V2 minus is on this reflected part is going to the port 1 as an incident, that is plus incident. So V1 plus dash will be equal to V2 minus. Understood? And so this V1 plus is the V1 plus dash will be the input port, the incident direction of port 2. So second coupler's port 1. And now coming to port 4 also same, V4 plus dash is equal to V3 minus. So already we know V2 minus and V3 minus in the above equation. So just substitute them and we will get V2 minus as this much and V3 minus as this much. So this is how we will write. So this is what we can see. So basically the phase difference between these two, second port of the second and third ports of the second coupler will be 90 degrees, and the difference between the amplitude is 0. So we feed a signal in a cascaded coupler. The output of the second coupler at the port will be 1 by root 2 times 1 by root 2 with the phase angle 0. At the port it is this, and here it is this, and the port is 1 by 2 with a phase of 90 degrees. So in terms of power, half of the power will goes to port 2 and half of the power will goes to third port. That's it. Now coming to the isolator. So how much time? It's 40 minutes. And now coming to the isolators. These are two ports non-reciprocal devices. These are two port non-reciprocal devices. So basically why these isolators are so much interested, because these act as a protecting devices. So I will tell you this in new place. Yeah, now coming to an isolator. This isolator is a two port device. Okay, there will be two ports. This isolator has a special property of like a diode, so that they will only allow in one particular direction. For example, if an isolator is designed to send signals from port 1 to port 2, this will be only sending the signals from only port 1 to port. If there is any reflected part or any signal trying to come from port 2 to port 1, they won't get traveled or they won't get reached this first port. Okay, so okay, by which what is the advantage? So let us take an example of a battery. Okay, let us take an example of battery plus negative. Now this battery will be connected to some network. So this let us assume that this battery is a non-rechargeable battery. Okay, non-rechargeable battery, where some signal, high frequency signal is sending and to this network. Due to some impedance mismatch, there will be reflection part of a signal, so that will come back to the battery. So as since these are very high frequencies that you are using in microwaves and all, that will definitely, radios or microwaves, they will be a very high frequency, so that means that that will definitely damage the source, EM source. Okay, so to avoid this type of damaging and all, so what we will do, the source, if it is this is a microwave source, will immediately connect an isolator to it. Okay, this isolator will be connected to the network. So what happens if there is only there will be flow on one side? If there is some mismatch happened and there is a reflection, it won't reach to the source, it will be absorbed by this isolator. So let's see how it works and what are the properties of an isolator. So for an isolator, so let us observe this diagram how it came, like the matrix. We can see that there is S11 is 0, that means there is no reflection in the port 1. Okay, first point, good. And the second thing is, when the signals go and 1 and S21 is 1, that means signal can go from 1 to 2. That's why it is 1, and that's why it has some value. Now next, coming to this, when you give in the input to the second port, what happens? It is S12 is 0. That means signal given to the port 2 is not able to travel to port 1, and also there is no reflection here also. That means S22 is also no signal won't be reflected back. Okay, so where it is going, you can see if I send a signal. Okay, if I send a signal to the port 2, either it should pass through, should reach the first port, or otherwise it should reflect back. But here nothing is happening, where it is basically they are disappearing. How it is done and all we will see in this explanation. So example of an isolator is like a Faraday rotation isolator. So Faraday rotation isolator is how it will be. There will be two, which inside the tube there will be ferrite material. So what happens, like why every time we will see that if there is a ferrite material, it is a non-reciprocal, because non-reciprocal, like what in layman terms what we can tell is, if a device is said to be reciprocal, it should able to supply all the, like it should act like, for example, if I use a device, okay, for example, if I let us take a resistor, if I give a signal to like one terminal, and it will definitely come out of the other terminal, and if I give it to the second terminal, it will come out of the first terminal. So basically it can use it as either way, but this isolator can't do like that. No, only one way. If you give the input to the first port, it will go to the second port, but it won't send the signal from port to the port 1. So how it is done, because inside that ferrite material, it will basically, ferrite means it is iron, so it will have some magnetic property, so due to which some magnetic will be introduced inside this coil, in this tube. As this electromagnetic wave also have magnetic fields in it, due to some repulsion or some attraction, what happens, this wave will be bent or twist, okay, twist to an angle. So this twisting of an angle will be depending on the amount of ferrite material that is placed on the and also and how much like strength of that ferrite material. Okay, see once, wait. So on this effect, as this twisting is done, this effect is called Faraday's rotation. Okay. So how much will be rotate will depends on the strength of the magnetic field, and also applying we are applying to the ferrite material as well as the length of the ferrite material. How much length, basically that how much length this ferrite material has kept inside the tube. So both two parameters will take place in determining the angle. So this concept of there are two factors by which ferrite materials will be rotate the polarization of electromagnetic signals. These are the two factors. So this concept will be used to construct an isolator, which is called as Faraday rotation isolator. So let us see the diagram. It is looking like this. Okay. So there are different kinds of Faraday rotation isolator. This is one of the this is okay. In this, what happens? This is some waveguide where we are twisted here at some point at a 45 degrees angle. So this is manual twist. No. So what happens, whenever you send, it will twist. Like if you send from this side, like port 1, or if you send from port 2, it will definitely twist. Okay. In which direction? It is only fixed direction. It will twist. For example, if I see, like I am telling, now I am sending from port 1 to port 2. The signal will be twist 45 degrees clockwise with respect to like when I am seeing through port 1, okay, in the direction of port 1. Now if I am sending a signal from port 2 to port 1, it will also it will be rotating in anti-clockwise direction. Okay, when at this twist, like in this point, at this point I am telling. So with respect to the port 2, when I watch the signal sending through the port 2, that signal will be rotated 45 degrees anti-clockwise. Okay. So that's why when you observe this diagram, as we are seeing anti-clockwise from port 2, definitely it will be opposite. No. So if you see this arrow from this end, now you are seeing, right? If I see behind the behind the screen, it will be seen like this. That's the variation there. So when I send, also let's see one by one. Now there will be one more component present, that is resistive card. You can see the shaded region here. So these are the resistive cards. Resistance cards what they will do, when a signal coming parallel to that resistive card, it will observe. Okay, if it is not parallel, it won't observe. If it is parallel, it will observe. So how it will be used? So when I am sending a signal perpendicularly, so what happens, due to first due to that ferrite material, it will be rotated. We need to one more thing you need to remember. From when a signal is going from port 1 to port 2, the signal will be rotated 45 degrees anti-clockwise due to ferrite material. I am talking about ferrite material. Okay, due to ferrite material. Now, okay, when the signal is coming from port 2 to port 1, it will be rotated in anti-clockwise only with respect to port 2. Okay, now so it will be also rotating anti-clockwise with respect to port 2. That's why we are able to see here it is rotated in this direction. When you are observing in this direction, it is looking like this, and here it is looking like this. So because I told you, you should see in the perspective of the input ports. Okay. So in the first case, I am giving the port 1 as input, so it is rotated anti-clockwise. So basically, they are generally when you give any signal in the ferrite material, it will rotate it anti-clockwise like that in this isolators. So with respect to the ports that are given you that you give the signal. Now first it is rotated 45 degrees anti-clockwise due to ferrite material, and there is a physical twist is there. So due to that, what happens, I told you, it will rotate in the clockwise direction. Okay, it will rotate in the clockwise direction, again 45 degrees twist. Now what happens, this was cancelled out. No, this 45 first it is anti-clockwise 45, now it is clockwise 45. So they will get, again it will become linear. So as this signal is perpendicular to the resistive card, so it will passes through the second port. Now coming to the signal given in the second port. First I given perpendicularly, so it won't observe. So it will go through here and it will suffer 45 degrees. What we call, it will suffer 45 degrees anti-clockwise. When you see from the second port, it will suffer anti-clockwise 45 degrees. Now what happens when as there is this ferrite material, due to ferrite material, whatever, again it will rotate another 45 degrees anti-clockwise. As I said, we should see from the port 2 side. So again it is parallel, no, 145 and again 145, total 90. So when this is the 90 degrees, I am rotated into one more 90, like towards the, it will be like this. So this is the 90 degrees. So this is parallel to the resistive card. So what happens, this resistive card will absorb this signal. That's why it is not able to reach the port 1. It is only stopping here, it is not reaching here. That's how it works. So this is how these isolators are working. So if they want to find this isolation and insertion loss, what is happening there, so the S matrix will be 0 1 1 0. Using that matrix, insertion loss will be 0.5 they have given, and isolation loss is 25 dB. So insertion loss using the formula, and what we found that minus 20 log S21, and we got S21 as 0.94, and isolation as 12, no, 12 we got as 0.056. So the new matrix will be this. Okay, remember in any matrix, okay. Actually these isolators are matched, no? That's why what happens, S1 and S11 and S22 are 0. That's why directly we wrote this 0 and 0. So basically these are the same problems, no difference. Now coming to the circulator. So circulators are basically a 3-port or 4-port devices. It has basically, if the circulator is 2-port, it is also called as isolator. So that's what, and a multi-port junction in which wave travels from one port to another. So basically it is like multi-port junction. So one signal, like if it is clockwise, no, if the, for example, it's a clockwise circulator, it will go from port 1 to port 2, and port 1 to port 3 it can go from port 3 to port 4, and it can go from port 4 to port 1. If it is anti-clockwise, the opposite directions. So for the clockwise circulator, the S matrix will be looking like this. This S matrix is lossless, non-reciprocal, matched in all ports. Circulators are non-reciprocal. Even it is a 4-port, it is a non-reciprocal, because we can't use a clockwise circulator as an anti-clockwise circulator. So this is how it will work. And now coming to an anti-clockwise, the S matrix for this anti-clockwise circulator will be looking like this. So the problems are the same. So they have given insertion loss, and one more thing, it is like here given is insertion loss they have given, and isolation loss is given. I think insertion loss we need to discuss once. So insertion loss is basically, it is a value where we will find for minus 20 log mod S21. Okay, there's a formula. So basically insertion loss is like port 2 to port 1, how much it is transmitted. Basically insertion loss can be related as a transmission kind of transmission, like when I given an input to the first port, what is the output at second port, or if I given an input to the second port, what is the output in the first port. So as we are given an input to the first port, we are finding only to S21. If in the question they have given that the input is given to the second port, then we will find S12. That's all. Now insertion loss and in the isolation loss, and you will given VSWR. VSWR is nothing but voltage standing wave ratio, that can be represented by a letter S. So we can find insertion loss and isolation, and also there is a formula for relation between standing wave ratio and also reflection coefficient, that is this. When you change the like, also we can write as gamma is equals to S minus 1 by S plus 1, where S is equal to 1.5 and we got gamma as 0.1. Gamma is nothing but S11 is gamma, S22 is also gamma, S33 is also gamma, basically reflection, no? So all this will be having 0.2, 0.2, 0.2, and remaining all the values are found using insertion loss and isolation loss. So this is circulator given, and this is like a radar and a transmitter like this. So what is the, so circulator is ideal and lossless. Okay, if they are given it is ideal and lossless, what will do? The circulator will be so the S matrix will be the normal S matrix what we study. Direct if it is a clockwise, generally it will take clockwise. So normal clockwise 0, 1, 0 like that only will take. But if a circle is non-ideal, then what you have to do? We have to use this S matrix and calculate the power of P3 and P2. So how you will find if I send a port 1 as an input, what is the power at port 2? So if I send at port 1, what is the power at port 2? Port 1 input, and I have sent some power P1, the port 2 output unit. So 0.85 whole square into input power of port 1. That's all. Input power as port 1 is I think that given so they are given the pumping of RF power as 10 watts. No, that is the power. So problem direction couplers. This is another problem. This is a normal problem only. Also this circulator. So this is okay. This is the last topic for these sessions. Hope you enjoyed, and thank you for watching. Like, share and subscribe.